Now that you've learned what rational exponents are and what nth roots are, we can move on to looking at properties of rational exponents. So I want you to dig in and pause the video if you have to, but I want you to look at this key concept here for properties of rational exponents. And look down this side of the list. And these should all look very familiar to you because you've seen them before. For example, you learned that if you had a power times another power of the same base, and you were multiplying them, all you would do was add the exponents. You also learned that if you took a power of a power, you multiply the exponents. None of these are new as you go down the list. You have the negative exponents property, the quotient property, and then you have the power of a quotient property as well. So none of that is new. But now the new part is, if you look on this side of the table, your exponents are fractions. So that's all that's new. So we're going to write exponents are now fractions. But the same rules apply, and so you should find these next examples not that challenging. So let's look at some examples. Again, if you need to pause the video and stare at that chart a little bit more, do so. Alright, so let's look at example A. They want us to use the properties of rational exponents to simplify this expression here. Well, I am taking the product of two powers, and I have the base number of 20 in both of them. And the rule has always been that when you have a product with the same base, you're going to multiply those exponents. So this expression can now be written like this: 20 to the power of 1/3 plus 1/12. And now this is where all those fraction rules need to come back to you, and you need to remember them and do not fear them. But when you have fractions with different denominators and you're trying to multiply or add them together, you need to get a common denominator. And so in this case, our common denominator would be the 12. And so for our first fraction, we would multiply top and bottom by 4 in order to get that common denominator of 12. And so this would turn into 4/12 plus 1/12. Alright, and then you simply add them together to simplify it, and you get 20 to the power of 5/12. Alright, and you are done with that problem, and you've simplified that expression. Let's move on to letter B. Here I have exponents that have different bases, 2 and 3, so there's nothing I can do with these right now. But I am taking this whole thing to a power of 6. And remember that you would sort of, quote, distribute that 6 to both of those powers on the inside. And so this expression would be rewritten as 2 to the power of 1/6, with 6 being distributed to that one, times 3 to the power of 1/8, and that then would be taken to the power of 6 as well. So then you need to simplify, and now we have power of a power. So here I'm simply going to multiply 1/6 times 6, and that is 1. And then you're going to multiply 1/8 times 6, which is the same thing as 6/8. And I'll leave it like that. So it's 3 to the power of 6/8. And now because you can reduce 6/8, you always should. And so you're left with 2 to the power of 1. You can write it or not write the 1 if you want. But 3, that power would be reduced to 3/4. Alright? And we would leave these like this because you've used your rational exponents to simplify the expression. You wouldn't take your calculator and finish it off, because what I'm looking for again is that you know these properties of rational exponents. Alright, letter C. You have two different bases, a 6 and an 8, and this is to the power of -1/1. Well, -1/1 is just -1 itself, and the same idea where you're going to apply that power of a -1 to each of those exponents. So you're going to end up with 6 to the -1 when you multiply -1 times 1, and you're going to be left with 8 to the -1 when you multiply that 1 here by the -1 outside. And then that rule still applies that you can't have negative exponents, so both of those get thrown into the denominator. So you're going to put 1 in the numerator as a placeholder, and now you have 6 to the positive 1 power and 8 to the positive 1 power. And this one you can simply just write 1/48 as your final answer. Here we have in letter D a quotient. You have 2 to the first power over 2 to the 1/3 power. So you have the same base. So remember the rule for quotients is you would end up subtracting the exponents. So it would become 1 minus 1/3. and I will just put parentheses around my exponents up there. And now you would use your fraction rules. You need a common denominator again. In this case, the common denominator would be 3. So I need to multiply my first term of 1 by 3 over 3. So this becomes 3/3 minus 1/3. And then when you simplify it, you get 3 minus 1, which is 2, over the common denominator of 3. And you are done. You have simplified this expression. All right, here are 4 guided practice problems using those properties of exponents. Remember, you know these already. They are not new, so rely on what your brain is going to tell you to do about these things. So pause the video and come back and check your answers. All right, here are the guided practice answers. Make sure, and I can't express to you enough, that if you get these things wrong, it is so important for you at this point to go back and figure out why you got them wrong and to clear up any misunderstanding you had, because these problems will only compound as you move on. So it is so important that you persevere here and figure out what you did wrong in any of these guided practice problems. All right, moving on to the next chart, I need to point out to you its title. This title is the properties of radicals. When we first started, we looked at the properties of rational exponents, and now we're looking at properties of radicals. And what this means, and if you recall, that any rational exponent can be written using the roots, the nth roots that is. And so now we're just looking at the other notation, the radical notation, when we're talking about any of these roots. So here you only have 2 properties, thank goodness. The first one is the product property of radicals, and that means if you're taking the square root or the nth root of any product of 2 numbers, that you can break this up into the nth root of each number and then take the product afterwards. It also works in reverse, that you could take this and turn it into that expression if you needed to. Then you have the quotient property of radicals. So if you had the nth root of some fraction, you could separate that into the nth root of the numerator divided by the nth root of the denominator. And again, this works in reverse also. You could take an expression written like this and put both, or the numerator and the denominator underneath the nth root. So let's dive right in and use these 2 properties and discover how they work. So example 3 I will write down for you. Our first example is we have the expression the third root of 125 times the third root of 8. And you could leave it like this and try to find a third root of each of them. That might be okay, but you could also multiply the 125 and the 8 together, those base numbers, and then you would come up with the third root of 1,000. 1,000 is just 125 times 8. And perhaps now when you look at it, you know what the third root is for 1,000, and that is what number times itself 3 times gets you 1,000, and its answer would just be 10. All right, moving on to another example, which I will write down. We'll call it example B. And this one is the 5th root of 96 divided by the 5th root of 3. And as we look at it, there really is no 5th root of 3, and you can't have a radical like that in the denominator, if you remember those radical rules way back when. But what we can do is actually take it and think of it as the 5th root of 96 divided by 3, because it serves our purpose well. So 96 divided by 3 ends up to be 32, and we're still taking the 5th root of that. And the 5th root of 32, the more you work with these, you'll start to learn what they are, but that is 2. So a repeated multiplication of 2 times itself 5 times would get you that 32. So let's move on and talk about then radicals in simplest form. And we've talked about this before, especially with square roots, radicals in simplest form, but now we have nth roots, so its index is n, or some number, maybe above 2. All right, and so they're considered in simplest form if the radicand, that is this thing, has no nth powers as factors in it, and I'll explain that to you in a little bit. And again, you can't have a denominator with a radical in it of any sort, so that needs to be rationalized if you remember this. So maybe I'll go back and I'll use an example when we had a square root, and we could do that. So let me just come up with one. Back in the day, if I had 28 under a square root, our number 1 job was to find any perfect square factors of 28. 8 underneath it. And we had a 4 times a 7, and we could see that the perfect square factor was 4. And so we'd say, what's the square root of 4? And your answer would be 2. And so the radical would disappear because we actually took the square root of 4, and we'd be left with the radical 7 still trapping that 7 underneath the radical. There's nothing to do to take that 7 out of there. So it's the same kind of idea when we're working with nth roots. So let's look at example A here, where we have the third root, of 56. And so there's two ways to do it. The one way kids mostly like is the prime factorization way, which is, remember, you're looking for 3 of any number now instead under the radical. So are there 3 factors that are the same where we can pull one out by taking its cube root? And so some kids like to use the prime factorization way, which is to take that 56 and start breaking it up into its factors until they're prime. And so 28 would be 7 and 4, and 7's prime, and 4 we would have to reduce to the 2's. So if we wrote it as a prime factorization under that square root, and we wrote down 2 times 2 times 2 times 7, well, you can see that you have 3 factors of 2 underneath that radical, and so we can pull one of them out. What this number really is 8, and we know that the cube root of 8 is 2, so that 2 is freed, and we are left with 2 times radical 7 as your final answer for this original expression, but now it's in simplest form. There's another way to do it. Well, let's look at example B first, and this one gets trickier because we are dealing with such big numbers. You can deal with them separately, though, and it makes it a little bit easier. So in looking at letter B, we have 2,144, the third root of that, times the third root of 2. Now, you could multiply these two things together. I don't really think it's helpful at this point to do that. The number one thing we need to do is do a prime factorization of 2144. So off to the side here, I will take 2144 and start breaking it up into its factors. And so I just used 536 times 4. You can use any two factors of your own. All right, and 536 then would get broken up into 268 and 2. And then 4 gets broken up into 2 times 2. And I like to circle them when I'm done. Some people bring them down with straight lines, but this is purely your own preference. So 268 gets broken up into 4 and 67, and 67 is prime. And I didn't mean to write a 6 there. Well, I had a little erase. Totally said 4. I know I did. So then now we can break that 4 up, and I've sort of run out of room. Oh, there, I made more. Break the 4 up into 2 times 2. So then you rewrite all of these factors underneath the third root, and you end up with 1, 2, 3, 4, 5 factors of 2. And then you have that factor of 67. And don't forget that we still were multiplying by the cube root of 2, which will just hang out there for a while. So now your job is to look for 3 of any repeated factors. So here I have 3 2's. 2 times 2 times 2 is 8. So the cube root of that is just 1, 2. And so that comes out. And then you look again for 3 more 2's underneath the radicals. And here I have 1, there's 2, and this is my third 2 if I put them together. And so that would be the cube root of 8 again, which is 2. So that comes outside the radical. And then that cube root of 67 is stuck under there. And so now you have pretty much simplified it, but you can multiply the 2 times 2 together, and you should, that we're on the outside of that radicand. So this is your simplified expression for letter B. For letter C, we could do it a different way if we wanted to. Let's look at it. You have the fourth root of 125 and the fourth root of 5. I'm still going to leave them separate, but I'm going to pull out factors and maybe show you that you don't always have to do a prime factor tree, that sometimes you can just factor it as it is. So if I'm looking at the first expression, which is the fourth root of 125, well, I'm just going to break up that 125 the best way I know how, which is 5 times 25, right? And right next to it you have the 4 times, or the fourth root of 5 as well. And so then I'm going to just continue on and kind of break those things up into factors. The 25 factors into 5 times 5, and then you have this fourth root of 5 still there. And so now when you kind of just break it up as you move along, maybe not do a factor tree off to the side, you can see now that I have 4 factors of 5 underneath, and so you could just immediately take the fourth root of that and you end up with the answer of 5, which is your answer. You certainly could have multiplied these together too, and then taken the fourth root of that, which is no problem. And just like back in the day when we worked with radicals to begin with, there is no one way to get to the final answer. The key is that you just get it simplified, and there's different ways to do that. So it takes a little practice, but you'll get comfortable with it as we move on. You may want to grab your book too and do some more guided practice problems on example 4 that involve getting radicals in simplest form. But this is something that we have done before. The only difference for you is to look for different numbers of repeated factors. So again, if you feel like you need extra work on it, grab your book and do the guided practice that has to deal with example 4. Alright, so we're going to kind of shift modes here really quickly and talk about like radicals. Just like you have like terms, those are terms that have the same variable part, you also have like radicals. And that means expressions that have the same index and radicand part can be combined as well. They can be added and subtracted, or you can use the distributive property on them. Here's an example right here, letter A. If you notice, I have 8, like a whole number, and then I have the 9th root of 7, and then you have 10, the whole number, and it's times the 9th root of 7. So these are called like radicals because they have the same index and they have the same radicand. They're both the root of 7, the 9th root of 7. And so we can put these together using simple addition, and the distributive property is technically how it's being done. But I can just add together my 8 plus my 10, and this final answer here would be 18 times the 9th root of 7 is how you would write that. And again, it's coming from the distributive property where you're actually factoring out its common term or common parts. That's the reason you're allowed to do it. So we'll do one more example. I'll just write example B, and that'll be 4, and I'm going to do this with rational exponent notation. So you have 4 times 9 to the 2/3 power. That could be written in radical notation, but I want you to see it in exponent, rational exponent notation. And you have 9 to the power of 2/3 again. And so again here you have the same, not technically radical part, but rational exponent part. And so you could just combine this simply by saying 4 plus 8, and you get your 12, and you could multiply it then by 9 to the power of 2/3. You would get the same answer either way. The answer would be the same if you did this and then plus this, or if you added the 4 plus 8 and then did 12 times that part. So example 6 is really the same as example 5. The only difference now is you're looking at expressions that involve variables, not just numbers, but the idea is the same, that if they have the same part, the same rational exponent part, that you can just take the coefficients of those and combine them. So you have negative 2xy to the power of 1/3 minus 12xy to the power of 1/3. And so because these are identical parts, you can take the coefficients of negative 2 minus 12 and combine those to get negative 14, and then you just rewrite down the rational exponent part, or the variable part in this case. It looks more like combining like terms in this case, but you really do have a radical expression there. It's a third root of y that's happening. Letter C, same idea, not a big deal. You have the same radical parts technically, y to the 3/5 power, so you can just combine the exponents, which is 5/9 minus 4/9. And so you could write this out, and I'll just do it like this. You don't have to write it out like that, but it's 5/9 minus 4/9, and then it's just times y to the 3/5. And using your knowledge of fractions, you take 5 minus 4 and end up with 1/9 and rewrite down y to the power of 3/5. This next example can get a little bit uncomfortable, but there's certainly examples that you are going to see in any test that you take and problems that you experience. So we're going to look at writing variable expressions in simplest form, and I'm going to write it down for you. Don't panic after you see it. Our first problem will be the third root of 6, x to the 4th, y to the 9th, and z to the 14th. Now that might look scary to you, but I want you to remember that all you have to do is find any 3 repeated factors, and you can take one out because it's the third root here. So we're going to write, just for your notes, that you can take out any 3 of the same factor. Sorry, this doesn't look that great when I'm writing it, but you can write it nicely. And so what I'm going to do is I'm going to keep in mind that I'm looking for 3 of anything, and I'm going to rewrite this expression in 3s if I can. Now 6 I can only reduce to 2 times 3 for factors, so I'm never going to be able to bring out a number from this, so 6 is just going to stay in there. Then I'm going to look at my x to the 4th, and I'm going to remember my exponent properties. I know I'm looking for 3 of those x's to come out, so I'm just going to write it as x to the 3rd times x to the 1st. Now, remember, if you multiply those together, you add the exponents, and this is really just x to the 4th right here, but I'm writing it in terms of a group of 3. So rewrite your variables in terms of 3's right now. Y to the 9th, I know I could make 3 groups of y to the 3rd, because when I add those together, I get y to the 9th, 3, 6, 9, and then I'm going to take z to the 14th and break it into 3's if I can. So I know I have 1 z to the 3rd, and if I do another one, then I have 6 z's, right? And I do another one, and I have 9 z's. And then I do another one, and I have 12 z's, but that leaves me with z to the 2nd that I'm still going to need in order to get my 14 z's. So I wrote it like this so that now I can look at it in a different way and realize that I can bring out this x. The cube root of x cubed is just x. I bring out this y. I bring out this y. I bring out this y after I cube root it. And then I can bring out 1, 2, 3, 4 z's. 1, 2, 3, 4 z's. Now what is still trapped under my cube root? Well, my number 6 is still trapped under there. There's no third root of 6. And then my x to the 1st power is still trapped under there. And so is this z to the 2nd power. So those cannot get out of that jail. And now the final move would be to put these back together and write them in terms of powers. It's just a prettier answer. So you have x to the 1st power, you'll have y to the 3rd power, and you have z to the 4th power, and then you are left with the cube root of 6xz squared still there. So it might look scary, but you can attack it with all the skills that you know about exponents and clean them up. There are certainly other ways to look at how we're going to bring out groups of 3. You might be able to look at it and just be able to tell how many are going to be able to come out and how many are still going to be left in, and that's okay. We have one more example that I need to show you. This is going to be about rationalizing the denominator. So let me add a slide and we'll do this one. So I'm going to write the problem down for you, because remember, you can't have a simplified expression if you ever had a radical in your denominator. So we'll call this example B for number 7, and I'm going to take the 7th root of p to the 8th power over q to the 5th power. And remember, you can write these separately, so I'm going to do that. You have 7th root of p to the 8th power over the 7th root of q to the 5th power. All right, and so now you look at that, and there's a couple ways to go, but my first way is I'm going to get rid of this denominator here with that has a radical in it. I'm not allowed to have this down here, so how do I get rid of it? Well, you need to understand that if I needed to bring something out from under here to make my seventh root go away, I need 7 things under there. But I only have 5, and we're talking about q's here. I only have 5 q's, but I need 7. So I'm going to rationalize this denominator by multiplying it by the 7th root of q squared. Why did I choose q squared? Because 5 q's and 2 more q's will give me those 7 q's that I need to rationalize it. Now, in order to make this a legitimate move in algebra, you have to do it to the numerator as well. And as long as you do it to the numerator and denominator, remember you are only really multiplying by the number 1, the identity property, and you're allowed to do that. You'll have the same answer as a result. So now that you've multiplied numerator and denominator by that stuff in red, you're going to end up with the numerator of 7, and then you have p to the 8th underneath the radical and q squared underneath the radical. In the denominator now, though, you have 7th root of q, and now you're going to add those, sorry, I even wrote it wrong. You're going to add those exponents, 5 plus 2, and you're going to get 7. The important part here is to focus on that denominator. The numerator still looks scary, I'll give you that. But this denominator now is a perfect 7th root. And so the 7th root of q to the 7 is just q. And you've gotten rid of that radical, and so you've done your job in the denominator. Now let's look at the numerator. We can simplify it more because I do have 7 p's underneath here. So because I have 7 p's underneath here, 1 p comes out and 1 p is left in. That makes your 8 p's. The q squared I can't do anything with, and that still just stays in there. So now you've taken this expression that wasn't simplified and reduced it and rationalized it and ended up with that simplified answer. All right, that is our lesson on applying the properties of rational exponents, but I did want to give you another resource in case you were having trouble with it, and that would be a Khan Academy resource. So if you went to www.khanacademy.org and searched in the search bar rational exponents and exponents laws, you will find another lesson from someone else, and sometimes it's better to hear it from someone else, on how to do these things. But I'll tell you, with practice, you will get good at them. Just make sure you get through them and don't give up. But if you go to khanacademy.org and search rational exponents and exponent laws, he does a really nice job of explaining this material as well.